Hello everyone, welcome to our presentation on web animations. My name is Doug Stockwell. I'm a contributor to the web animations specification. I'm leading the implementation in Blink, and I work in the Google Sydney office.
Hi, I'm Shane Stevens. I'm also working out of the Sydney office. I'm one of the editors on the specification, and I lead the team in Sydney for web animations. The rest of our team's here as well, so say hi, guys. Yeah, thanks, Mike. Yes. So we're going to break the talk today up into 4 pieces. First, we're going to give you a little bit of a background about where the idea for web animations has come from and who's been pushing it. Then we're going to talk about the all-important topic of shipping. In particular, I'd like to have a little bit of a discussion of our recent intent to ship. After that, we'll talk about what it actually is that we're shipping now, what we plan to work on next, and some stuff that's going to come a little bit later. And finally, we're going to do a little bit of a deep dive into our implementation, and there's going to be some awesome diagrams. So a bit of background. The web's had declarative animation via SVG since SVG 1. The feedback on the SVG animation stuff has been that it's a little bit difficult to use. It's quite complex. It gets complicated very quickly. It's somewhat overwhelming. Possibly in response to that, Apple introduced CSS transitions and CSS animations in 2007. These are both very, very simple. They're very easy to use, but they're also somewhat underpowered. They don't provide a lot of features that increasingly web developers have been asking for. Now there's a task force which is part of the W3C, the FX task force. It's formed of members from the CSS working group and the SVG working group, and it's tasked with harmonizing the parts of CSS and SVG that happen to overlap. They are now interested in the features in SVG animation and the features in CSS transitions and animations being unified. That's what we're doing, and we're also adding a JavaScript API to expose all of these animations primitives to JavaScript directly.
So this is what we have today. There's a specification. We've published 1 working draft, and we're expecting to publish another really soon. The specification is being actively worked on by Google, Mozilla, and Adobe. The spec's still very large, but we're working very hard to cut it back down to the set of features that browsers are first going to be shipping. We have a polyfill, a fully featured polyfill, in fact. It supports all major browsers. It tracks the spec very closely, and it lets people start using web animations today. Up until now, this has been the way that we and other developers have been able to test out our API, to experiment with different options, and just to see like what works, what doesn't work, just to try things out. Oh, thanks, Shane. So just some background on Blink. Last BlinkOn, I talked about where we were going, and the plan was to move animations and transitions to the web animations model. We did that late last year. Not many people noticed, which I guess was surprising because we really did replace a lot of code. And just a couple of weeks ago, we sent an intent to ship and flipped on the flag to ship a very small subset of the web animations API.
So I'd like to talk about this shipping of the minimum viable product for a little while. We've just said that the specification isn't finished, and yet we're going to ship some stuff. And I want to concentrate a little bit on why we're doing this. So in the particular case of web animations, as we heard this morning, it does provide a number of features that developers have been asking for, and it does so in a way that lets them use those features performantly, which is not currently possible with CSS transitions and animations. So I think there's a real desire for some of these features and a real need, and it's important that we get them out there now rather than waiting for the spec to fully stabilize. The spec has been around for nearly 2.5 years now. We're not ready to progress to LC yet. There's a number of the more nebulous features are still really being worked out and nailed down. And I think in general we need to balance specification stability with a few other concerns. So there's things like experimentation, the ability to do testing out in the real world, getting things in front of developers, and of course timeliness, getting things out on the web at the point where they're needed. On the other hand, the specification effort is really important, and definitely in the case of the web animation spec, having a specification with multiple companies, multiple different people working on the spec has produced a much better result than anything that we could have done alone. So we need to reconcile those two sort of conflicting concerns, and we're trialing a solution that we hope will help with that. The idea is to identify a minimal subset that we want to release, try and keep it as small as possible while offering useful features, ship it, listen to feedback, listen to what people are saying, accept the risk that we might need to change things, make any changes that we need to make, fix things, and then wash, rinse, repeat. So just take a small piece and then another small piece and another small piece, and make sure that we do continue to get things out in front of developers without just throwing a whole bunch of stuff out at once. And an interesting point here, we've worked really, really hard over the past 2.5 years to gather feedback from people. So we've sent emails to PublicFX detailing multiple different approaches for various spec points and asking for input. We've sent emails to www.style, to BlinkDev. We've had Twitter conversations with web devs. We've reached out to authors of JavaScript animations libraries and asked them to have a look at our stuff, to tell us what's missing, what's needed, what works. We've published multiple articles on HTML5 Rocks. Brian Birtles from Mozilla has a blog, and he's published multiple blog articles about web animations. And we've got feedback. We've had a trickle here, a trickle there. We've had people make comments. Some of the comments have been really informative and really good. We've had a lot of very positive feedback. But sending an intent to ship has been by far the single most successful approach that we've found to gathering feedback. I don't know if that's a failing of our community, but it's an interesting point. If you really, really need feedback for a feature, threaten to ship it. And I think it's also important to note that we're not doing this in a vacuum. We have discussed the phased approach to releasing quite extensively within the spec team. And we've identified sort of phase 1, which we think is very concrete and is unlikely to change, a phase 2 that's a little bit more nebulous, and a phase 3 that's kind of, a lot of work is required. We've talked about the idea of releasing things iteratively, and it's had a lot of support. So we're not just going out and doing this alone. We've talked with people about doing this, and there's been a lot of positive response to the idea.
Okay, so coming back to what we're shipping right now, here's a really quick example. We've added a new Animate method to Element. So in this example, you can see we're passing in some keyframes where we're changing the transform. There's some timing parameters. We're setting the duration. You can set other things like the easing, iteration count. And later on, we can come back and, given the player which was returned from Animate, we can cancel it. That's about all we're shipping right now. But these are actually very powerful features. So while the animation is defined by script, it's still declarative, which is kind of unlike regular JavaScript animation using request animation frame. The difference here is that basically you've described exactly what you want to do. You've said, here are my keyframes, here's my timing information, go and do it. So this means that if you animate something like opacity, transform, or filter, we can go ahead and run those off the main thread on the compositor. They're just moving things around, like Nat explained earlier a little bit. This also solves some other problems that people have been running into using things like transforms. Again, as Nat talked about earlier, when you call Animate, you start an animation. You don't need to force a style recalc. You don't need to insert, generate a new style sheet, insert into the document, insert into the DOM with all the expenses that costs. It just happens. And likewise, the animation plays. It's guaranteed to finish. If you subscribe to a finish event, you're guaranteed to get a callback. So you don't have to worry about the additional expenses of things like forced style recalcs. Just one other point on that. We don't actually support filter yet. So a decision we made earlier in shipping was that we don't want to put more content on the web using prefix properties, and filter is still WebKit prefixed. So the Web Animations API calling element.animate, it just will ignore anything with a WebKit prefix right now. So coming up next, and all of this stuff is actually implemented behind experimental features. There's a lot of polish left to do, but we'd like to start shipping the rest of phase 1. And this includes things like playback control. So being able to pause a player that's running, reverse it, set its current time. Actually, setting the current time is really an amazing capability. So here's a quick example of what this could do. Think about an ebook reader where you've got like a page turn animation. So you can imagine, like, you call element.animate to animate the page turning. Great. But on a mobile device, you might want that feature to be a bit more sophisticated, where you can actually drag the page turn. So basically what you could do then is listen to touch events. As the finger is moving, you're basically just setting the current time on a paused animation. Following on from there, you can, as the finger is released, just resume normal animation playback. So that's really quite a powerful feature. The second important thing that Playback Control enables is better synchronization. So this is something you haven't really been able to do before with CSS animations, aside from maybe just starting two animations at the same time and hoping that they do actually play in parallel. Imagine that you're animating something across the screen, and some event happens in your application that means you need something else to be exactly aligned with that running animation. You'll be able to start a new animation, understand exactly the exact point in time at which the previous animation is running, and synchronize your new animation immediately with that. Another part of phase 1 are these additional methods on element and document, which allow you to acquire handles on the active and upcoming animation players. And this includes not just those animation players generated by script, but also those that have been generated as a result of CSS animations and transitions. There's a number of reasons why this is really useful. First of all, it allows us, maybe for the first time, to really be able to test that CSS animations and transitions are working. So we can write a test where you call element.animationPlayers, you get back a player that explains, what a CSS animation is doing. You can look at its timing, you can see how it's functioning, you can seek it and see if it's interpolating correctly. This is a great feature for testing. It means we can write tests that run across different browsers. For authors, this is interesting because it allows them to start an animation in CSS, but then obtain a web animations handle on it and seek it and do all the other kinds of things I was talking about, but they don't immediately have to switch completely over to our API to be able to start such animations. And another useful thing here is that this is perhaps really interesting for building tools. You can imagine that being able to obtain the active animations would let you build something like an animation inspector, where you can see what's happening on the page and be able to tweak it and things like that. Something else we need to start working on a bit more is widening compositor integration. So far, we've mostly been working within the confines of the existing compositor API. But this was really only designed for CSS. For more advanced features of web animations, it's really far too narrow to be able to do things efficiently. And there's just some weird cases that in WebKit just weren't supported, even for CSS. Things like if you started an animation that was using step timing functions, that meant it ran on the main thread. If you specified fractional iterations, it ran on the main thread, just because that API only accepted integers. So there's plenty of work that we have to do there.
Okay, and then after we've done that important work for phase 1, there's a bunch of other things too that we want to do to basically build out the future releases that we're going to do behind it, the experimental flag. So we've got things like an animation constructor that is just another way of putting animations together. We've got groups that let you build up quite complicated declarative models of animations with parallel playback, with sequential playback, and lots of nesting. We've got custom effects that let you run, define your effect as a JavaScript method, so that your animation actually calls out into JavaScript on each frame. Motion paths, which are ways of letting you move HTML content around the screen along beziers, arcs, and line segments. Additive animation, which lets you define multiple animations that apply on top of each other rather than replacing each other. Deeper CSS integration, so that we can provide more idiomatic access to CSS structures like keyframes objects without having to go through the CSS OM. Media integration, so that you can integrate audio and video tracks as part of your animation. And of course the SVG integration work, so that we can fulfill the FXTF's request to unify all of the different declarative animation types on the web platform. So a lot of this stuff is available in our polyfill right now. The animation constructor, groups, custom effects, motion paths, and additive animation are all working there. And I think we'll have a lot of it available through the experimental flag inside Chrome pretty soon. So as I mentioned earlier, feedback is great. We'd really like early feedback about a lot of this stuff. If you want to check out our polyfill or check out our implementation and test out these features, tell us what's missing, what works, what doesn't work, that would be really, really helpful and would help us take the spec in the right direction rather than just have to basically keep guessing about a lot of this stuff. So we're going to do a bit of an implementation tour now. We'll give you a brief overview of the model and how it works, how the pieces of the spec are exposed in code, and then we're going to do 3 crosscuts through the code itself. We're going to talk about timing updates and how they propagate down from a timeline through animations. We're going to talk about exposing animation results inside CSS and the hairiness that results there. And we're going to talk about interpolation itself, taking values from the API and turning them into things that can be applied inside styles. We promised you some awesome diagrams, and here's the first one. Yeah. Okay, so you can see at the center of this diagram we've got the animation object. And an animation is basically constructed of 3 pieces. It has a target, which is what it applies to, an element. It has timing information that tells you how long the animation runs for, how many times it runs, what kind of easings apply, all that sort of stuff, when it starts. And then it has an effect, which is what it does, what properties it changes, and what values it changes them to. There are 2 kind of ownership concepts that are exposed here. You can see that animation timelines right at the top of the diagram hold on to players. Players are the things that play animations and show them on the screen. And players have a source, which is a timed item. Animations are a subclass of timed item. And so this is the way that we pass timing information, timing updates down through the model to update animations' understanding of where they are. The other ownership concept that you can see here is that elements maintain a list of active animations. This isn't actually required by the spec, so we've put a little cloud around active animations to say it's more of an implementation concept. But this is how styles are reapplied back into elements. So where timing comes down through the animation timeline and player, style updates come down through the element and active animations. And Doug will talk about these 2 concepts a little bit more in just a minute. And then you can see at the bottom with the effect that we have at the moment just keyframe animation effects, which have a list of keyframes that define the way that the animation will, or the properties that the animation will change and how it will change them over time. And this is the interpolation stuff that I'll talk about once Doug's done.
Okay, so once we've created some animation objects and players, timing updates are the way that things happen, things come out of them. So there are really 2 kinds of timing update that happen in the system. The first is basically the heartbeat of the system. On each animation frame, the compositor or the Chromium compositor, CC, is sending us a time value, and we push that down through the tree. And I'll talk about that in a bit of detail on the next slide. The second of these is an on-demand update. So basically any other time that we need to bring animations up to date. So these would include things triggered from script, like get computer style, or any time you touch offset top. We need to ensure that animations are up to date. So we do an on-demand update for that. Okay, so I'm going to explain just quickly how time flows down through the system. So up at the top left, we have the Chromium compositor, and it's passing us a current time value for the current frame. And our job is to ensure that animations are basically synchronized at that time. So this time gets passed to the page animator. This diagram's not entirely accurate, but the basics are here, which ticks the animation clock. And the animation clock is something that basically ticks every frame. So it advances, at 60 frames per second, every 16.6, it'll tick 16.6 milliseconds. The page animator asks the animation timeline to do an update. So animation timeline pulls the time back from the clock, iterates over all of its active players, and passes that time down. The players do some basic calculations to determine their current time. So things like playback rate can affect what their current time actually is. Once they have that, they pass that down to their source timed item. Timed item runs a bit more complicated timing logic and calculations to do things like apply easings and other timing parameters, and basically produces a time fraction and current iteration. So fraction is like how far we are through an iteration. And the current iteration is just which iteration we're up to in an animation. So in the case of an animation uses the fraction and iteration to determine what the effect should do. And it passes this information to the effect. The effect can go ahead and speculatively cache its results at that point. And if the animation's in effect, it will go and notify the element that a star recalc's needed at some point. All this work is generally deferred. So the star recalc will happen usually, in this case, at the end of the frame. Oops. So animation's kind of intimately involved in star recalc for a couple of reasons. One is, like as I just mentioned, that's kind of like, we've got an effect to apply, so we said to the element, you're going to need to do a star recalc to apply your effect. But also because CSS animations and transitions are just CSS. CSS says, we need to run this animation, this property transitions, and so they both generate and apply within star recalc. So what I've got here is just a snippet that's kind of deep down within star recalc that summarizes how we fit in right now. So the first thing here is apply match properties, which is just the regular steps in star recalc. We've figured out that these properties apply to an element, we apply them. We do adjustment, and adjustment's basically ensuring certain invariants about the render style. So it goes and does a bunch of little fix-ups. And we have to do that before we do all the animation work to avoid starting transitions between an adjusted and unadjusted render style. We actually made a mistake initially, like before we shipped, fortunately, and yeah, it's not good when you do that because you just keep doing stuff. It's bad. So once we've adjusted the render style, we can go ahead and do our animation work. We need to come back and fix up the render style again in case we had violated those invariants. But even this, looks good, okay? But we're not done yet. The CSS working group is still in the process of figuring out exactly where animations and transitions should apply within the cascade. One possibility is that they'll actually come back in before important properties, which means a lot of this would need to change. We might need to push animations back into apply match properties. We might need to do this work twice. It's just not really clear what's going to happen. And it's different between all implementations right now. And I think this is interesting to think about because CSS animations and transitions have been kind of around for many years now. So it's just interesting to think about, like, they're shipping. So within apply animated properties, I just want to explain, exactly what happens there. One thing to note is, so what we're going to do in the first step is basically to produce a update which explains what's happened in terms of animations and transitions. And this update, we're just building a data structure. We're avoiding mutating any animation-related data structures. That's good for the modularity of our code, but it also enables options in the future, like if we were to, say, make star recalc parallel or threaded in some way. And basically what we're trying to do here is we're just looking at the old render style and the new render style, and for transitions we're going to say, oh, that property specifies it transitions, does it match? If it doesn't match, then that's a trigger that we need to start a transition. And you can kind of see here how some of the problems that we face with transitions or authors face with transitions where unless we have a star recalc to notice that difference, if they were to then go ahead and set it back to the original value without having a star recalc happen in the meantime, we would have never started a transition. So that's just some of the issues that happen when authors use transitions. The process is basically the same for animations. We're just looking at which names of animations are specified currently, which were specified previously. Anything that's new gets started, and anything that was removed gets cancelled. Animations have the additional complexity that they can be paused and unpaused. So once we've built that information about the CSS animation update, we can go ahead and think about how we need to apply the results of animations, so their effects, and the effects of any new CSS animations that have started. So what we do is we do this process called, we resolve the animation stack, basically. So we take the information that was in the CSS animation update, we combine it with information about active animations. So we do a merge, we sort in priority order, we figure out exactly which interpolations apply, pull those ones out, and apply the results directly to the render style. So once we're completely finished with the star recalc for an element, we can take that animation update which we generated, which basically says what starts and stops, and we can apply that to our data structures. And all this is really doing is using the API, but internally in C++. So it's saying, create a player, start the player, cancel that player, set pause on that player. And I think this is a really good sign that the spec is able to explain how CSS work, or CSS animations work in terms of an underlying model. Just the fact that internally we're just using exactly the same primitives that developers will be able to use in the future.
So the last area that we're going to talk about today is interpolations. Interpolations are an abstraction that we use to represent simple linear blends between two values. We've had a little bit of an evolution in terms of getting to this representation. And I'd like to just sort of explain where these things have come from, why they're the way they are, and talk about some of the complexities with them. So when we took on the task of building the web animations model into Blink and replacing CSS animations and transitions, replacing the existing approach, the way that approach worked was it would capture whole render styles from the start of a transition or from before a style update, and then do a render style to render style comparison to decide which transitions to trigger. And for animations, then there would be a render style generated for each keyframe, and again, you do a render style to render style interpolation. So the code that implemented this was full of templates. There were lots of getters and setters that reached directly into the render style. It was there was a huge map of registrations from CSS property ID through to the particular implementation you were supposed to use for that property. And we weren't confident that we would be able to take that and build it out to support all of the features of web animations. So we introduced a new concept called animatable value. And an animatable value is basically a unified representation of the various platform values that end up in computed style. So an animatable value could be a platform length or a platform transform list or even just a simple opacity value. Unfortunately, that still doesn't go far enough. So while animatable values made it a lot easier for us to build our initial model and to get CSS transitions and animations supported, we realized that there are a number of cases that were required by the API that we just couldn't support with animatable values. And this includes things like interpolating values that exist at specified value time, things like ems that are sensitive to font size, but that get removed by the time you get to computed style. So we came up with this new concept of interpolations and of interpolable values, and that's those that I'd like to talk about. So this demonstrates the process of converting keyframes down to interpolations. You can see at the top you've got something which is reasonably similar or quite similar to the at keyframes representation that you can use in CSS. Each keyframe optionally contains some or all of the various properties that are being animated. Some of them, but not all of them, may contain offsets that say where that keyframe falls inside the animation. And this is a good representation for authors, but it's a bad representation for computers. So we need to do a conversion and normalization to property-specific keyframes. Once we get to property-specific keyframes, we have a channel for each animating property, and we have a keyframe inside that channel that is specific to that property. So in this particular case, you can see the left channel has 3 keyframes because there are 3 different left values in the top representation, whereas the top channel only has 2 keyframes. And we've also filled out all of the missing offset data so that everything's nice and regular and easy to understand. We then do a further transformation of that into interpolations, and each interpolation represents just a single linear blend between a start value and an end value. So we need 2 interpolations to represent the left channel, one to take us from 0 to 0.2, and one to take us from 0.2 to 1, and a single interpolation for the top channel. And you can imagine, you can also see that there's a little bit of timing information stored in here as well, or at least offset information, and you could imagine, maybe you can't see that, it's quite small. You could imagine a time fraction coming in and using the time fraction to sort of pulling out just the interpolations that are currently active, wrapping those up and handing them off to style recalc to actually do its job of putting the results of these interpolations into the style. Interpolations are a little bit deceptive. They seem like they should be really simple, but they turn out to be a bit more complicated than we thought. So we've actually worked out that there's 4 phases in interpolation. There's conversion, interpolation, deconversion, and application, or cider, which is also my favorite drink. The advantage of separating this up into stages like this is that it makes the code a lot more modular. We can reuse a lot of pieces, and we can cobble together interpolations that perform different tasks. So the example that we've written out here, interpolating from 30 pixels to 15%. In the first stage, the conversion stage, you throw away all of the information that isn't useful to the actual interpolation itself. So we know that we can't just directly interpolate 30 pixels to 15% because they're different units. But we don't actually care what the units are. So we represent 30 pixels as 30 and 0, and 15% as 0 and 15. And then when we do an interpolation, we have these 2 independent channels that are both interpolated to in this case, their halfway point. That's the interpolation phase. After that, we need to do a deconversion back into a platform value that is recognized by style application. In this particular case, we build a calculation value, which is the platform representation of calc. And then application puts that into the style. And depending on what you deconvert into, there's a number of different application approaches that you can use. There's the existing style builder that takes CSS values, our animated style builder that takes animatable values, or you can directly do a style.set something if you have a platform value. And then there's a number of complicating cases that make it worthwhile to do this split up. So for example, 50ems, which we talked about before, we can't just turn 50ems into a pixel value and interpolate that, because then our animations will stop being responsive to font size changes. So we maintain that information during conversion, we maintain it during interpolation, and then it's only at the point where we do deconversion, which happens just before we apply that value into the style, that we throw that information away. Another example is inherit. You can't do anything with inherit until you actually have the computed style that you're doing the animation for, because you need to read the inherited value out of that style. So if you're animating to or from inherit, you have to actually defer conversion, interpolation, and deconversion until you're right at the end in application. But for example, if you think about a keyframe animation that goes from inherit to say 50 pix to 100 pix, well, you need to do all of that extra work for the first interpolation, the part between inherit and 50 pix, but then the interpolation between 50 pix and 100 pix, you don't need to do any of that extra work, right? And that's one of the advantages of treating each of these segments separately. We can take that second segment, boil it right down to a really simple description of interpolating between numbers, and it should be really, really fast. Additionally, for those cases, we can do conversion once up front, whereas both of the previous approaches, both animatable values and render styles, render style comparison, we actually had to do conversion of the values that we read out on every single interpolation. So we think that this approach is going to end up a lot faster. So I think I hope we've managed to communicate the new animation primitives that we're adding to the web, both now and in the future. We've given you a little bit of a tour, a fairly high-level overview of the internals of the way things work. I guess a couple of things that are really worth mentioning. First of all, we're actually, if you're interested in the release issue, if you're interested in the discussion of when it's a good idea to release or how to release stuff on the web in a timely fashion, we are having a discussion session tomorrow called Releasing Experimental Features, which we'd love to see you at. Come along and voice your opinion. That's not specific to web animations. That's just in general how to manage releasing experimental features on the web. we really do welcome any questions or feedback that you have. If you want to volunteer to help work on the spec or the polyfill or the implementation, we'd love to hear that too. We'll be around the rest of today and tomorrow. Just come and talk to us, and hopefully we'll be able to answer any questions that you have. I think that was. Yep. So thanks very much for listening.
Thanks.
And I guess if you have any questions now, we'll be happy to take them.
I'll yell, "Can you hear me?"
Yes.
Okay.
Thanks. You mentioned using that you could have an animation that was driven by input, and I thought that was really interesting. Can you imagine a point that we could get web animations to the point that it's expressive enough that we could re-implement all of scrolling as a input-coupled animation?
Yeah, it seems like that should be possible. There are a number of interesting cases inside Blink where we actually do animations that aren't coupled to the animation engine, like scrolling. I think that's definitely something we could do. Other examples are things like, there's an HTML5 progress bar. I don't know how many people use this, but it's an interesting case where it has a timer, and every so often it just updates how it renders. But the scrolling case is interesting, and I think there are other possibilities in the future for further levels of web animations where we can make the coupling between events like touch and how they drive an animation declarative, so that instead of you don't have to listen to every event and decide how that impacts the animation, but there'll be some way of coupling those together.
And then execute on the impl thread instead of the main thread?
Ideally, yes. And there's probably lots of options for, like, right now it's just transform, opacity, and filter that happen on the impl thread. But we can do more than that. Yeah.
Cool, thanks.
So on a somewhat related note, all of the work you're doing is touching style, which means that on every frame you're going to have to recalc style, redo a bunch of layout, figure out repaint, etc. Do you have any sense that you might be able to identify things where you can sort of just set it and pass it all the way down to the painting code, to skier, or to the compositor to just play it out without having to do all this stuff at the top?
Yeah, so I didn't talk exactly about how. So we do have compositor animation right now for those properties that I mentioned, but I think definitely yes. In the future, if rasterization is faster, then having some way of, like, let's say we're animating the background color or something, or let's say we're animating the color of border. If we have some way of expressing that entire model that says this border is somehow coupled to this animation, I think we can definitely do something like that.
Yeah. So, sorry, just to confirm, compositor animations are active right now, and for the properties that the compositor is currently capable of performing quickly, all of that does hook up. So if you're animating a transform or an opacity through web animations, that does run on the compositor, and it doesn't do a style recalc on every frame.
Okay, and then a related note is, does the player object have methods to query the current interpolated value out of the system, and how do you deal with that with something that's going to the compositor?
This isn't in the first version of the specification. It's a request that we've had before. I'm currently very, very interested in getting this into the specification, but obviously, it's a matter of all of the editors agreeing that it's a good idea. It's great that you brought that up, though.
It seems really, sorry, it seems hard to implement. I know. So I come from the SVG. I've seen the SVG animation code and worked in that, and a large part of the complexity of that comes from you being able to query to basically JavaScript to be able to reach in and find out what the current values and things are, which means you have to maintain all this infrastructure while you're animating to answer the query. And I'm just curious how that would work out in this case.
I think we would do something somewhat less complicated or somewhat less complete than what SVG does. We'd let you query an individual animation's contribution to a result, but not necessarily the the result at the stage where that animation is executed. So you'll be able to get individual contributions plus through computed style final result, but not sort of intermediate pieces, if that makes sense. Did you?
I just wanted to also mention that I guess for an animation that's running, just the way the platform is built right now with things like get computed style, you do have the ability to query, like, what do things currently look like, And there's an interesting story behind how that worked in Blink and previously WebKit, where it was actually a special case for compositor animations. So if you were running a compositor, if you're animating transform and you said, get me the computer style, get me the transform value, it would just advance the animation to the current time, which isn't really what's displayed on the screen potentially at any point. So what we're trying to do is move to a model where, so that animation clock that I mentioned, ideally that ticks as the compositor ticks, but we don't always get told about that. What we'd like to do is move to a model where it basically is a prediction, ideally with a lot of support from the compositor, as to like what the next frame time will be. And so if you query the if you call get computer style, we might advance animations to that point in time, which will ideally be what is displayed. There may be other ways of like having synchronization points. So for example, if you query the current state of an animation during a request animation frame callback, as long as that callback is committed to the compositor, then you have a pretty accurate measurement of where we're at in the animation.
Great, thanks.
So have you considered more integration with the dev tools with animations, like you'd see the list of active animations and maybe step through them?
We definitely want to do something that we haven't had many conversations about that yet. One thing that we have done is in Sydney we hosted a couple of interns, and we just kind of let them loose with web animations, Polymer, web components, all that stuff, and they actually produced a really cool tool, which basically can create animations, see what's going on, visualize them, all kinds of interesting stuff. And I think it just shows like how easy it could be to build some really great developer tools. But to date, we haven't really started on doing a serious developer tool.
We might integrate, if we do have a developer tool of sorts. I think the developer extensions would probably be a good place to start thinking about doing an integration there as well, rather than building it directly into the dev console.
Although I guess some things that could be useful in the developer tools, like built-in, are things like, because we have this problem right now that you start an animation, and depending on exactly what you did, it may or may not run on the compositor. So it might run the main thread, it might run the compositor. But currently there's no feedback to the developer about exactly what happened. So being able to visualize, oh, this animation ran on the main thread for these reasons is something we'd like to do at some point. Okay, thanks everybody.